Okay, so this is number 1 on the practice version of the second exam. So we have to do some more integration problems. So the instructions, as you can see here, are just to integrate the following. So one thing that makes these a little bit weird is that these are what's called improper integrals because they have infinity here instead of a number. So that's the trick, is how do you deal with infinity. So let me remind you. You replace infinity with a letter, like I like to use t. And let's just change this. What is this? This is the same thing as 2 times x to the minus 1.1 dx. Okay. So just take the antiderivative as you normally would. What would happen? It's just the add 1 rule, right? So 2 times, what happens when you add 1 here? You get x to the minus 0.1, and you have minus 0.1 here on the bottom also. And the limits go from 1 to t. Okay, so let's plug t in here, and kind of simple. Let me simplify this a little bit first. The same thing as minus 20 times x to the minus 0.1. Okay. So you can pause the video and figure that out if you want. So where does that come from? It's because negative 0.1 is the same thing as negative 1 over 10, and then the 10 flips out, right? So you kind of see. And let me put the limits here, and I will plug t in to x. So when I do that, I get minus 20, and I get t to the minus 0.1. And now I have to do subtraction, but I subtract a negative, so it becomes plus. And I plug 1 in for x, and that just gives me 20. So t, quote unquote, was infinity, right? So how do we deal with that? The way we deal with that is, now that we have everything worked out for t, we take the limit of this as t goes to infinity. So that kind of makes t infinity again. Alright, so what happens when we do this? So forget about 20, the only thing you have to look at is t. So t is getting to be a really big positive number, and you can see that t is raised to this negative exponent. So let me just remind you what that means. Let's just look at t to the minus 0.1 for a second. This is the same thing as 1 over t to the 0.1, or if you'd rather think of the exponent as being 1 over 10, you could do that too. So you probably know what happens. This is like the 10th root of t, right? So t is getting really big, but we're taking its 10th root. But that doesn't matter, because if you take a really big number, the 10th root of a big number is still big, right? So if I take the 10th root of, what should it be, 10 billion? What's the 10th root of 10 billion is 10. Though it does makes it really smaller, but then, if the number is big enough, then even the 10th root will be huge. So what's happening is, as t goes to infinity, is that this thing in the denominator here is growing big, and then when you have 1 over something big, it gets closer and closer to 0, right? So the effect of taking this limit is that this first part goes to 0, and you're just left with 20, okay? And so that means that 20 is the answer, for one thing. And it's kind of interesting. I mean, we just showed that if I drew a picture of this curve, let me see if I can erase this stuff here. So if I drew a picture of that, what would it look like? It basically just looks like 1 over x. I mean, nobody can draw well enough, or I can't draw well enough. I can't even draw close to well enough to make this look anything different than just kind of the way 1 over x usually looks, like this. So we go from 1, and the infinity means that we go all the way out, and then it turns out this area underneath the curve is 20 units. Super fantastic. So let me push this down, and we'll do the second one. Alright, so maybe I'll do this one in green. So I could have done them both at the same time just by replacing 1.1 with like r or something, right? So what have we got? We've got to do the integral from 1 to t, and I'm just going to write this as 2 times x to the minus 0.9 dx. Did I write my dx last time? I hope so. Okay, so what happens when you take the antiderivative here is you get 2 times. Now what happens when you add 1 to negative 0.9? A little different, right? So when we added 1 to negative 1.1, we get a negative number, but now when we add 1 to 0.9, we get a positive number. So that you'll see that that's important later. So now instead of negative 0.1, I have x to the 0.1. And I still have my limits here. So let me go ahead and oh wait, I forgot to divide by 0.1, didn't I? Yeah. Okay, so this becomes 20 times x, and the limits are from 1 to t. Why am I, sorry, I'm such a drug addict. I'm not actually literally on drugs, it's just behaving as though that were the case. So it's x to the 0.1, and the limits go from 1 to t. So plug in t, so I have 20 times t, and just like before, we can think of that exponent as being 1 over 10 if we want. And let's take away what happens when we plug in 1, which is, sorry, it froze for a second. So let's take away what happens when you plug in 1, you get 20. Okay. So just like before, now t is kind of like infinity, right? So we want to take the limit as t goes to infinity of 20 times t to the 1/10 minus 20. Okay, and so what happens here? Well, we can make an argument that's kind of similar to what happened last time with the 10th root of t. The 10th root of t gets really big as t gets really big, and so what we have here is infinity minus 20. It's kind of like infinity minus 20 is still infinity. Alright. Great, and that's the answer. So the answer to B is infinity. Let's kind of compare what happened in these two examples, something kind of strange. So if you graph them, or if you draw the graph, you'll notice that the picture is exactly, it's practically exactly the same for both of these functions. It's just the picture of the hyperbola, the picture of 1 over x, and in both cases we go from some number 1 and we go out to infinity. And in the first case, the green stuff here turned out to have area 20, and in the second case, the area under this green stuff turned out to be infinite. And notice that the only difference between these two is that this is x to the 0.9 and this is x to the 1.1. And this might remind you of this fact about these improper integrals, that the exponent 1 is a really critical cutoff point, right? So the integral of 1 over, this 2 isn't going to make a difference about it being infinity or not. So if you look at 1 over x to the p dx and you go from 1 to infinity, the only way this is finite is if p is greater than 1, and it's always finite when p is greater than 1. So you need p greater than 1 for this area under the curve here to be finite. And that's going to be a good thing to know, because something kind of analogous to that is going to happen with infinite series when we start looking at those this week. So that's how you do number 1, and that's all there is to it.